Okay, so now that we've done the make the projector work dance, let's start. So my name is Kastel. I work at Intel in a group called Open Source Technology Center, and I'm a part of a team that is focused on finding security bugs in open source software that ends up in Intel projects. Since Android is one of our projects, I'm going to share with you how we've done some bug hunting that is related to media on Android. For the agenda, I will give a brief introduction about what file fuzzing means and what are the requirements to be done before you start testing and how all the bugs can be trashed and find what is unique and make your life easier in finding crashes. So as fuzzing basically is just a black box testing technique. You just send corrupt, invalid files to one end and see what gets onto the other and how the system rejects the files that are corrupt and what are the reactions of the system. Basically, you are targeting to have any kind of security-related issues up to denial of system and total freeze of the system. Usually, fuzzing can be applied to any application or system that accepts an input, either by files or by ports, or as long as there is a parser for the input, fuzzing can be applied. The tricky part is that when you have a protocol or a complex application where you have to be very specific in how you define the input. Otherwise, you'll be sending input and it will not be accepted by the application and will be rejected instantly. As a walkthrough, you need to prepare your data. You need to have a target, and the target you must be sure that your input goes straight to what you are trying to test and is not rejected otherwise. All the issues must be logged and saved so that you can perform an analysis afterwards. And it will be nice, especially if you are doing some testing on open source software, to ethically disclose all your findings so that the community can benefit of the fixes also. Okay, so why audio and video? Well, these are the types of input that require the decoders are big in number of lines of code. It can be very complex to decode some specific media type, and also there are a lot of applications and codecs. And at some point, everybody starts to take something and optimize it, thinking that their version will be better than the others. And this way, a lot of errors are introduced. And also, there is a common belief that media files are usually harmless. There isn't anything there bad that can affect my system. And you don't need specific requirements from permission system to open a media file. It just opens it, and there is no need for root to open a media file on any other system. Okay. For Android, we've built a list with all the files that are accepted. I mean, type of coders, type of containers, type of bitrate, and made a list. And after that, based on this specification, we've started to build in files. We've tried to look straight to what is decoding the files and to avoid all the Java virtual machines and all the Java applications. And we were interested to go as deep in the system as possible so that we get close to the application. And of course, you have to monitor where the crashes are and save them, and be sure that you avoid all the false positives that might take time to find. So in the past couple of months, there was a media buzz about stage fright and all the vulnerabilities. Stage fright is a media framework that contains a lot of libraries, and those libraries are kind of they still need a lot of work. The advantage in testing this framework is that it comes with a command line interface. Using this command line interface, you can just say, okay, this is the file. I want you to decode it using this decoder, and either to specify, okay, I need you to use software, hardware, and see how it goes. So it's very pinpoint accurate, and it makes things very simple. You can uh, you can generate data input for your application by basically in two ways. You either take a valid file, which is mutational, and you start bit flipping it and saving each iteration of that process. This is the most simple way you can do it. The second option will be to use the generation way. You take the files requirements, file specification, and you say that okay, the first 5 bytes are the header, the next 5 bytes are data, and all that, and you mark in your tool, okay, you can fuzz only this part of the file. And this way you are sure that the code coverage increases and your results are more accurate. Based on what I've said, this list of tools is listed on, how should I say it, complexity of the tool in usage and in features. The first one, Zizuf, is just, you give the target, what is the application that you want to test, you give the input, and the ratio of how much fuzzing should be applied to a file. And it will start running and saves all the crashes and all that. And by ratio, I mean percentage of the file that must be bit flipped. Then it starts one by one and flips all the bits you've said, and you'll see how it goes. The second one, it's a project from CERT, and it comes with a virtual machine, which you install, which is an Ubuntu-based virtual machine. You install your application there. You have to do some configuration about what kind of testing you want to perform, and it comes with it has some monitoring features where it goes and checks the state of the machine, and if it's freezing or doesn't respond, it just reboots the machine and starts the whole process again. The last one is an instrumentation-based fuzzing. So the source code is instrumented and built, and it goes to specific points in the binary and marks. And if those points have been touched by the input, it starts to modify the input so that it can go deeper in the source code. And this way, you can increase the code coverage and make use of the tool. When we've run this process, we had a separate machine that was crunching the data files, and it was saving the file, generating, saving, logging, taking the results after the machines, perform the triage, and so that we don't interfere in the running in the production system. We had the second line was a local machine, which was taking patches of files and sending to the devices. It was keeping also the state of the devices, monitoring, taking the crashes out, and if one of the devices was crashing, it was just rebooting the system and continue the run. In a period of 8 weeks, we got to the point where we had around 11 terabytes of data. So the files aren't that big; they are a couple of megabytes of size. And the idea was that we generate this volume of data so that we can increase the code coverage. As for the logging part, Android comes with a specific system for logging. It's called Logcat. It has different levels of usage. You can put stuff related to debugging and high-level issues, and you can insert whatever you want there from your application. And we leverage this Logcat, and we've started to print what we are running, what are the crashes, what is the file that crashed, so that we can afterwards take the logs and parse and see what were the issues that we found. And if you start doing this type of testing and everything goes well, you'll have this type of errors. Most of them are not quite exploitable, but it's recommended that you just go into the source code, read it, what is around, and see how where is the problem, and maybe you can find some other issues. And using those 11 terabytes of data and around a cluster built out of around 20 Android devices, and in a period of 8 weeks, we got to the point where we had around 185,000 crashes. And at this point, we said that, okay, it's not possible to manually filter all these issues. And so that I don't think any human being would like to go and to look in all these issues. And we found that we need to do some automatic triage of all this stuff. And we've built a mechanism that was taking the crashes, every crash was retested so that we can avoid false positives. And I mean, the devices were continuously running, and maybe the context of which the device was, there may be a false positive. So we have to retest all those issues to see if everything was clear. And based on the information in the tombstones, we filter some the information needed so that we can make sure that the combination in type of error and the program counter where the error it's unique, so that we can build a unique database of files. Android helps by saving all these core dumps in two places. And we took these files, we put it with the tombstone and also the file that caused the crash. We saved them and so that we can have in the same place. And based on this information, we were able to filter all those crashes so that the number of crashes will go very, very low. And at the end, we got to the point where after 8 weeks, we had around 185,000 crashes, and we also built a triage mechanism, and we've started reporting issues to Google. And it took some time before we got all the CVEs and the issues to be fixed, but in the end, the improvements have been added to the Android, and now it's difficult to find new issues related to this. So the tool that was used for this process is available on GitHub. It was open sourced this year, and people started to commit to it and add modifications and started to include it in their process, in their testing. I'll be around here for today and tomorrow, and if you have questions, you can ask me, or otherwise get an email and drop me an email, and I'll try to respond as brief as possible. And if you guys have questions. I'm not aware what's happening in Windows.
Yeah,
I'm working in
they're opening the source. It's going to be co-chair program. So I was thinking, do you know something about this?
No, I'm in Open Source Technology Center, so we are dealing with open source stuff and all operating systems or flavors of operating system that are used based on Linux, and on top of that, so Windows is out of my range.
Okay, thank you.
Yes. So I have a couple of small questions. First, how you actually generate the data? Because you told that you use the mutational fuzzer or AFL. Are you using AFL for these numbers?
AFL, we've started to introduce it recently, so all this work was done with mutational fuzzers based on a high number of files. We've started to using bit flippers, so you just take the file, switch it in binary, flip a bit, save it, and this way you get a lot of files. And AFL, we've started to use it recently. With AFL, we used for starting with AFL, we've used the files that were causing the biggest number of crashes in the previous sessions, and those files that were having the biggest code coverage. And we started to put those files into AFL, and this way we can leverage all the work that we have done before and not use.
So where do you get the first test cases, the first files? You have a database with a large amount of...
There are some internal repositories where we have media files that can be used to testing. you can use this, you can use stage fright to test software and hardware. We were more interested in how the hardware decoders worked. But since we've seen that, hey, we can use this also to test the software stack. Okay, let's just throw it there and see where it crashes.
So finally, which is more or less the number of distinct crashes that you get once you filter?
So I forgot to mention here, but the number of distinct crashes were around 40.
40.
Yes, out of those 40, we had only 4 that got the CVE, and there were high security issues. The other they were different, like we had different heap exhaustion, also integer overflow and stuff like that, that were not very easy to exploit or caused any damage. And one of the good parts of testing this on Android is that the stage fright is not only used on Android, and it could be all those patches were pushed to the other software. Like there are a lot of them which are using stage fright.
Okay, thank you.
Okay.
I wanted. Oh, sorry. I wanted to ask whether you tried to exploit the vulnerabilities you've identified.
So we've tested on the latest version of Android, and it will be kind of, so when you're playing with a heap and try to use it remotely, it's kind of a bit difficult. And we've said that it will be more, we could gain more if we just use that time into finding other bugs. So we just find, okay, this could be exploited, just report it, and that's it.
So basically, your work stops as soon as you can control the.
Once we get to write, once we could write in memory, we said, okay, that's it.
Okay. Thank
We
you.
stopped.
Hey, cool presentation, nice. One question, how do you categorize the crashes in order to see if they are exploitable or not?
The fastest way you can find if a crash is exploitable, there is a tool for that. There is an app for that. There is Bang Exploitable, the name of the tool. It's also, there's a version for Linux and a version for Windows. And based on it takes the core dump, and based on the information in the core dump, it has an XML file. And if it finds something familiar, it will just say with an appropriate, okay, this might be exploitable, this might not be exploitable. So it basically has a list, something like that. And it takes, based on each type of error, okay, these are not exploitable, these could be exploitable, you should look into it.
Okay, thank you. And another question, for instance, if one person at his home would try to reproduce your work, what resources would he need?
So he will need time and a lot of knowledge about what is in the Android OSP3. Because you don't have access to the stage fright command line interface by default. It's not a binary which is installed in every Android image. You have to modify the source code and so that you have the binary and the end with all the testing interface. And after that, you will need some processing power to generate all the files and a lot of devices if you want to gain some time. Otherwise, it will take some time to parse a couple of terabytes of data. But it's doable.
Okay, thank you.
Have you tried looking into other means of mutating the media files? I mean, you talked about bit flipping. I was curious whether.
So AFL comes with a series of fuzzers. It goes by bit flipping 1, 4, 8 bits and all that. And after that, it has some let's say mathematical ways in which it starts to bit flip and compares the code and see if new paths have been taken, and based on that it continues. So yes, we are looking into that.
I was when I asked you this, I was thinking about. I'm not sure if you're familiar with Frankencerts. I think that's the name. They've basically used this technique for fuzzing HTTPS libraries, or TLS libraries, to be more precise, where they, I mean, given the complexity of a X509 certificate, they're basically taking bits and pieces from different certificates and feeding those as input. And I was curious whether you tried this on media files.
On fuzzing for certificates, that's another story. It's nothing. There is very little information from this that you can build on that because you have handshakes, you have formats, you'll start to build the requirements of that certificate and start to arrange bits in that order so that the certificate will be valid, and it's totally different, and it can be done.
Yeah, but it's another, let's say, technique. Yeah. So I was curious whether there's other techniques you use besides bit flipping.
You have to take some tools from here, and you can take the fuzzing part out of it and apply it to the certificates and define what can be fuzzed or not. And after that, you have to recalculate all the checksums and all that. So it's different.
Did you try your fuzzing files on different hardware platforms, phone brands? Like, did you find any hardware bugs?
So for the hardware decoding stuff, we're okay. we went briefly on that, and it's we managed to survive all the stuff we've tried there, but at least until now we didn't find anything.
But you run your test on different phones, different brands of phones, or only one maker of phone?
We were only targeting devices that were using Intel x86 platform, so that was it. But some of the software, some of the issues that are related to software decoders are available for all range of platforms.
Okay, thank you.
Okay, guys. So if you have any more questions, look for me around here, and thanks for your time, and I hope you enjoy it. Thank you.